First of all, I would like to thank the organizers, especially Dr. Silva, for this opportunity. My talk focuses on a set of results obtained during my PhD studies. These are related to forbidden energies and forbidden couplings. The first question is, what does it mean? To answer this question, let me provide a brief introduction. The fundamental question in spectral theory is how the spectrum of an operator is modified under perturbations. In this setting of regular perturbations, the following results were proven in this paper. In this statement, angle brackets denote inner product in H. So we call for forbidden energies to the elements in spectrum of A denoted by sigma, which are not eigenvalues for any regular perturbation of A. Also, the elements in Z1, where sigma p denotes the set of eigenvalues, are called forbidden couplings. So, a question that arises is the existence of results like this for the case of rank 1 singular perturbations given by this formal expression where phi is a generalized vector. That is, phi lies in H-2 but not in H according to the A scale of Hilbert spaces. And angle brackets denote the duality pairing between H-2 and H2, or simply the action of linear functionals. In this direction, Barry Simon answered this question in his outstanding paper from 1995. For the case when phi lies in H-1 but not in H, that is for so-called form-bounded singular perturbations. The case addressed in this talk is regarding for unbounded singular perturbations. That is, phi lies only in H-2. The difference between the two cases lies in the fact that in the first one, the formal expression A alpha determines only one operator. On the other hand, in the second case, A alpha turns out to be a biparametric family of operators, A alpha C, where each operator is determined by an extension phi C of phi. Another difference is the corresponding approach. In the case when phi lies only in H-1, is used the Formson method, while in the case when phi lies only in H-2, this method fails. In general, a classical approach to describe rank 1 singular perturbations is by means of self-adjoint extensions of a densely defined symmetric operator with deficiency indices 1, 1. See, for instance, this classical monograph by Alberto and Kurasov. In this line, it was proposed to prove forbidden energies and forbidden couplings for the setting of von Neumann's extension theory, and forbidden energies lie for the setting of boundary triplets theory. From the first item, the main results for rank 1 singular perturbations are concluded, whereas the second one is interesting in the abstract sense into the self-adjoint extension theory. We have the definition of support and topological support of a positive Boyle measure. The next proposition was originally formulated for a certain class of measures by Del Rio, Makarov, and Simon. We extended for a larger class. This actually means the original proposition holds for measures integrating the function 1 over 1 plus absolute value and therefore finite measures. It requires properties of Borel-Stirling transforms. Now, it is extended for so-called quasi-finite measures. In this talk, V will be a densely defined closed symmetric operator on a Hilbert space H. So we define regular points for V where vertical lines denote norm in H and capital I denotes the identity operator on H. We will call efficiency spaces to the sets so defined where this symbol denotes orthogonal complement in H, RG and curl denote range and kernel of an operator respectively. We shall use this notation and we call the efficiency indices to be the pair so defined. Next, we have the von Neumann's extension theorem, which says that each self-adjoint extension of V is uniquely determined by every unitary operator between the efficiency spaces of V. This result can be seen in this textbook. Now, suppose that V has the efficiency indices 1, 1. The vectors U plus minus are called efficiency vectors. For each theta in this interval, we define the unitary operators V theta. By von Neumann's theorem, we denote the self-adjoint extensions of V as T theta, where domain of T theta is given by this direct sum and acts of this way. So we denote by H0 the cyclicity space of U plus for any T theta, which by definition is the closed linear span of this set. It was proven in this classical paper by William Donoghue that H0 does not depend on theta and is a reducing subspace for T theta. Therefore, we have the restrictions T theta to H0 acting on H0, which are self-adjoint operators and have simple spectrum since, by definition, U plus is cyclic for T theta reduced to H0. This is due to the following. First, by definition, U plus is cyclic for T theta if H is equal to H0. In addition, the cyclicity space of U plus for T theta reduced to H0 coincides with H0. So from now on, we will not assume that U plus is cyclic. Why? The reason is the following. The literature on this topic is claimed that the extension from the cyclic to general case is trivial. Despite this, it was decided to analyze what actually happens when U plus is not cyclic. This gave rise to the following theorem, where theta 0 is fixed and mu capital 0 is defined through the spectral family of T theta 0 reduced to H0. To prove it, we only verify that the restrictions of T theta to H0 coincide with the self-adjoint extensions of the adjoint operator to restriction of V to H0. As corollary, the eigenvalues of every restriction of T theta to H0, excepting theta 0, are the points where the function G converges. Applying the above results, we get a theorem on forbidden energies for the restrictions T theta to H0. It suffices to see that this set called Alberto spectrum is equal to topological support of mu capital 0, and that the points which are not eigenvalues for any restriction of T theta to H0 is just the complement of the set from the last corollary, and by the previous proposition about dense G delta property, this theorem is proved. Now, in order to lead us to the following key result, the next proposition is required. This statement is relied on a result of this paper by Alexandre Gordon. Its proof follows the same line. We concluded the following theorem on forbidden extension parameters. We simply substitute this set Y in the last proposition for intersection between Alberto spectrum and the union of eigenvalues of all T theta reduced to H0 excepting theta 0 and take its complement. Moreover, as in the case of regular perturbations due to the invariance of the absolutely continuous spectrum, we conclude the following result. I will now present a generalization regarding forbidden energies in the case of finite deficiency indices. We say that a matrix-valued measure is a function omega from the family of order subsets of the real numbers into the matrix space n by n on the complex numbers satisfying these conditions. In order to get a forbidden energies-like theorem, the following result is required. This symbol means convergence. This one denotes divergence, and topological support of omega is defined like in the scalar case. We remark it is a generalization to the matrix values case of the aforementioned dense G delta property. Next, we have the definition of boundary triplet for B adjoint. We denote by AI to the self-adjoint extension of B whose domain is kernel of gamma I and define closed proper extensions of B. Also, we say two closed proper extensions are disjoint if this holds. Keeping the previous definition in mind, we state the extension theorem by boundary triplets, which says that every self-adjoint extension of B is uniquely determined by each self-adjoint relation on K. Now, the following are well-known facts. The first item is a necessary and sufficient condition for the existence of a boundary triplet. Even dimension of K is equal to the deficiency indices of B. The second one, for the case of finite deficiency indices, says the parameters for the self-adjoint extensions of B disjoint from A1 are Hermitian matrices. Next, we define the Weyl function corresponding to a boundary triplet phi as the function M, where ρ denotes resolvent set and B bold denotes the space of bounded operators on K. Also, we define completely non-self-adjoint operators. Since the eigenvalues of the self-adjoint extensions of a symmetric completely non-self-adjoint operator have multiplicity at most the deficiency indices, we can define eigenvalues of maximal multiplicity in this way. Now, we present this result by Malamud, which generalizes the classical theorem in the Aronside-Donoghue theory on characterization of eigenvalues to the setting of finite efficiency indices. It states that the eigenvalues of maximal multiplicity of a self-adjoint extension AD of B are the points satisfying these conditions where omega comes from the Nevalina-Herglotz representation of the Weyl function F. We have the following corollary, and finally, the forbidden energies-like theorem is concluded. The same procedure as in theorem on forbidden energies is followed. A spectrum of A1 plays the role of Alberto spectrum, which is equal to topological support of omega, and we apply the generalized density delta property in this corollary. Now, if A is self-adjoint and semi-bounded, we define the A scale of Hilbert spaces, where H negative S, called negative space, is the completion of H respect to the norm negative S, or the space of linear functionals on HS. So we obtain results that characterize the negative spaces. To this end, we reformulate the definition of operator in the generalized sets. Originally, the operator A to the minus S over 2 is extended from H to H negative S by density. In the proposed approach, we view the operator H to the minus S over 2 as a mapping from H negative S into H via the Banach adjoint operator of A to the S over 2 and the Ruiz representation theorem. Now, when A is non-semi-bounded operator, we consider the scale of Hilbert spaces on modulus of A plus identity. This yields different characterizations for the spaces H negative 1 and H negative 2. We now define resolvents in the generalized sense by applying the aforementioned approach, which provides equivalent norms in both H negative 1 and H negative 2. Now, in the theoretical framework of round 1 singular perturbations, a question of interest is to obtain self-adjoint realizations of the formal expression A alpha. To this end, the following lemma by Alberto and Kurasov is fundamental. It states that the restriction of A to the kernel of phi is a densely defined closed symmetric operator with efficiency indices 1, 1. By the above result, we can consider the self-adjoint extensions θ of A point. Now, in summary, the Kurasov-Alberto approach is as follows. The expression A alpha is an operator defined in the generalized sense from H2 onto H negative 2. To obtain domains in H such that A alpha takes values in H, it is required that the functional phi extended to the domain of A point adjoint, which requires that expression 2 be well defined. It is possible if phi lies in H negative 1, but if phi lies only in H negative 2, this is generally not possible. Therefore, expression 2 must be renormalized. That is, a value is assigned to it. Then, for each real number, there exists an extension of phi to the domain of a point adjoint, and hence an operator A alpha C, where the parameters alpha, C, and theta are related by formula 3. By the results on von Neumann self-adjoint extensions, we obtain the main theorems for rank 1 singular perturbations. In these statements, the vector u phi a plays the role of the efficiency vector for a point. If we fix a value of C, the first theorem follows directly from replacing A alpha C with T theta according to the previous result, and applying the theorem on forbidden energies for self-adjoint extensions. This second one is proven from the fact that the extension parameters theta corresponding to the self-adjoint extensions of A point are transformed into coupling constants alpha for the rank 1 singular perturbations of A via a homeomorphism determined by formula 3. And theorem on forbidden extension parameters is applied. We conclude the existence of singular continuous spectrum for a density delta family of rank 1 singular perturbations of a self-adjoint operator. And when the parameter C varies, the set 4 is dense in the plane. The results presented here will be submitted for review and publication. Thank you so much.